for the invitation. I love coming here. I'm going to be speaking about a project that's in progress. It's based on a paper with my former student, Francis Bischoff, and Maxime Zabzin. And I'm going to be speaking about a paper joint with these two, and also some recent work with Francis. Okay, and it has to do with quantization of generalized Kähler. Now, in order to explain how this thing works, there's a lot of moving parts. It's like one of those gizmos that has, you start the ball and the ball rolls and goes around a loop and hits dominoes, and then those hit other things. It's a kind of many moving parts. So in order to explain how it works, I need to explain to you about Kähler manifolds first, the usual Kähler case. Okay. So let's say that there is a type of quantization for usual Kähler. Okay. So let me explain some aspect of the quantization of Kähler manifolds. So suppose that we have a symplectic manifold. Okay, so how do you quantize a symplectic manifold according to geometric quantization? What you want to do is produce a vector space out of it. Okay, and so the first step is pre-quantization, where we find L, or let me call it U, over M, a complex line bundle. You have a Hermitian metric, okay, and you have a unitary connection whose curvature is the symplectic form. Okay. And then the idea is that you want to take flat sections of this line bundle. But, of course, curvature is the obstruction to finding flat sections. Because of the fact that you have curvature, you cannot find flat sections. So it fails. Quantization is impossible. Okay. So instead, what you do is you say, well, omega is in omega 1, 1. So it's of type 1, 1, which is inside all forms. Okay. And you notice that the curvature is not 0, but the component of the curvature in 0, 2 is 0. So this means that L, or this bundle with connection, it is actually flat, but only in certain directions. In T01 direction. Okay. Now, what did I do here? All of a sudden, there's these 0, 1, 1, 1, 2, 0. Where did this come from? It's not part of the symplectic geometry. All of this came because I chose a complex structure. So all of this is a complex structure on the manifold. The tangent bundle splits into the minus I and plus I eigenspace of the complex structure. And these are the two directions that I can use to analyze the curvature. And so this thing is not flat, but it is flat in the holomorphic or the anti-holomorphic direction. And so it makes sense to obtain now a vector space of flat sections. So it's now I can look for flat sections in the 0, 1 direction. And this is usually denoted as H0 of x with respect to I, H0 of m, u. Holomorphic sections. Okay. So this is how quantization works. We obtain a vector space. Okay. Now, so there's something important about this. So this is called a polarization. This is called polarization. And we needed to choose this polarization in order to obtain this vector space. And so you may wonder whether the vector space depends on the polarization. So in other words, this is not just a quantization of m omega, it's a quantization of m omega with this polarization chosen. Okay? And so there's a famous theorem which explains that if you deform I, then the resulting H, so if we deform I to some I of t, then H0 goes to HT, and there is an isomorphism between them. So this is sometimes called Hitchin's projectively flat connection, or that goes by various different names. The idea is that this does not depend in an essential way on the polarization choice. So it's independent of polarization. So this is somewhat imprecise because it does actually depend. It could depend on it, but maybe not under small deformations. Maybe if you did a large deformation, then maybe it would depend. But anyway, I'm not talking about this. So there's a further step that you could take, and this is an important step. So let's quantize omega, but also 2 omega and 3 omega, 4 omega, and so on. Okay, so I want to produce now a sequence of vector spaces. So what we get is this is the quantization of omega, and this is the quantization of 2 times omega, which would involve, so this involves H0 of u. This involves H0 of u tensor u. Okay. And I can produce the quantizations of all of these symplectic manifolds in a similar way. Okay. And the point is that when you do this, the Hilbert spaces, I'm going to ignore the Hilbert space structure, just these vector spaces, these quantizations, they assemble into an algebra. So we get a Z-graded algebra. Okay. Now, what is this Z-graded algebra? It's this holomorphic sections of u, u squared, u cubed, and so on. Okay? And this is very well known in algebraic geometry. This is the homogeneous coordinate ring. This is the homogeneous coordinate ring of the complex manifold. Okay? And this is dependent on the polarization. In fact, it completely contains the polarization. It totally encodes it because it knows about the complex structure. So you see that although the individual spaces involved in the algebra, the kth graded component, is independent of the polarization, this algebra contains completely, characterizes the polarization. Okay? And this is what I want to do. So I'm going to abuse geometric quantization. Instead of using geometric quantization to get a single vector space which doesn't depend on the complex structure, I am going to abuse it, produce this algebra, which does depend on the polarization, because I'm interested in studying the polarization. Okay? So this encodes, the algebra encodes the polarization I. Okay. Okay, and the main idea that I want to explain in this talk, the idea is that we can take this data of a symplectic structure and a complex structure, and we can deform. So this is a Kähler structure, and I can deform this so that it's still symplectic, but the complex structure is deformed as a generalized complex. Okay. Now, deformations of I as a generalized complex structure, okay, these are given by a certain cohomology group, and that cohomology group is I can just write it out. It's H0 of wedge 2t plus H1t plus H2 of O. Okay, so here this is deformations of complex structure. So what I'm trying to say is that normally when we deform the complex structure, this is where the deformation lives. But I'm going to deform this to a generalized complex structure, and so there are two additional components that we can deform in. This is the gerb, which I'm not going to focus on this, and I'm not going to focus on this. I'm going to focus on this. This is the non-commutative, in quotation marks, deformations. And this is the Poisson structure, sigma. Just 1 second, 1 second. So the main idea is this, that I'm deforming the Kähler structure so that the symplectic structure remains symplectic. The complex structure becomes generalized, and I'm deforming it by a Poisson structure. And the point of this is that we want to obtain the same result. We want same result. We want a Z-graded algebra. Okay? So in other words, this thing is interpreted, this, just as it was here, is interpreted as a polarization data. And what am I quantizing? I'm quantizing omega, 2 omega, 3 omega, 4 omega. Okay? I'm doing the same quantization, but I'm using a different polarization, and I will get a different algebra, because the algebra encodes the polarization. And the question is, and this is the unsolved problem that has been around for so many years now, how do we obtain a non-commutative algebra from a generalized complex structure? And the claim is that this is one way to do it. Okay, that's the idea of the project, of the talk, and so on.
In this Kähler case, maybe it's the algebra structure, I don't know, but if I just take one big power of H,
yes, yes, then it still doesn't depend on the polarization. No, there's no complex structure. It doesn't depend on the complex structure. It's only the algebra. For the Kodaira embedding, you need to have the algebra structure, right? You need to have the coordinate ring structure to know what the algebra is. If you only have... Yes, correct. Yeah, the algebra of functions. You want to take the Z-graded algebra. Those are all sections of all powers of the line bundle. You pull it back to the manifold, and you interpret those. If you divide them by each other, then you get the sheaf of functions. Yeah, but without different powers, without different degrees, you don't have anything. Didn't Rui ask a question? No. Yeah.
So there's also a choice in the line bundle.
That's true, but it's for my purposes, let's say that the Picard group is discrete, so it's just a topological choice. Yeah, I mean, you could imagine some Kähler manifolds where it's not the case, but let's ignore those. Okay, so the complex manifold? If you wish, if you want to think of the homogeneous coordinate ring as an actual ring of functions, then you could take the total space. But in algebraic geometry, they're perfectly happy with homogeneous coordinate rings. In other words, they're twisted functions, so they're okay with that. Okay. Okay, so this is the program. So what we need to do is see what happens to this whole picture when we deform the polarization. I'm going to try to escape the camera. I'm going to try to move faster so the camera cannot catch me. Okay. Okay. The problem is that there is no analog of so this idea of taking holomorphic sections. So if I deform the complex structure to a generalized complex structure, you may have thought that maybe the generalized complex structure has a Dirac structure corresponding to it, and it has some kind of, this idea of taking the flat sections in the 0, 1 direction and to take the holomorphic sections of U. You would think that there was a direct analog of this, so that we could just take generalized holomorphic sections of some of this line bundle. And we never have been able to find such a thing. So there is no, as far as I know, any direct analog of taking holomorphic sections of U once I is deformed to a generalized complex. Okay? So this is that's one problem. And the other problem is that the product on the algebra does not come from the tensor product of sections. Okay, so if you take a section of U and another section of U on the manifold, and you tensor them together, okay, that is, even, so that is not the source of the multiplication. This would be commutative if we did this, and the algebra is not commutative. It shouldn't be commutative. And in any case, we don't even have holomorphic sections of it. So there's many problems, but these are the two main problems, that we don't have an analog of holomorphic sections, and we cannot expect that the algebra comes from just tensoring sections of the line bundle, of the pre-quantum line bundle together. We need something else. Okay, so we need to rewrite H0UL in a way which generalizes. Okay, so this is the key step. So we did not know how to do this until this paper with Francis and Maxime. The paper with Francis and Maxime from last year is important because it explains how to re-express this space of sections in a completely different way. Okay, so how to write H0 MU in terms of symplectic geometry. Okay, so step one. I'll just give you a step-by-step procedure in order to obtain this vector space in an alternative way. Okay, so we start with the cotangent bundle of M. Okay, so we're going to double the space, and now we're going to start with the cotangent bundle. Okay, now what I want to emphasize is that it's very important that this is the holomorphic cotangent bundle. So I'm using I to produce this. I'm using the complex structure. I get a holomorphic symplectic structure. This is the canonical holomorphic symplectic form on the holomorphic cotangent bundle. Okay. Then, number two, we do the magnetic deformation. Yes.
So M is Kähler to start?
Yes, we're starting. I'm just talking about a Kähler manifold. Yeah. Yeah, I'm just redoing the thing on the left-hand side. So the problem is that this is now expressed in a way that does not deform. So I need to re-express this in a way that does deform. Okay, so I'm going to do now a magnetic deformation. I'm going to define a new two-form, which is the old two-form plus the pullback of the Kähler form. So whenever you take a cotangent bundle, right, and you take a two-form on the base and you pull it back and add it to the two-form, that's called adding a magnetic term. So it's a nice way of understanding how particles behave under magnetic fields. You could just change the symplectic form and then just do Hamiltonian flow by the same function that you normally do, and this is how the dynamics changes when you turn on the magnetic field, which is given by omega. Okay, so now what we've done is deformed omega naught to omega. So this is no longer a 2-0 form on T star M. It's no longer a holomorphic 2 form because I added something which is a Kähler form. It's of type 1-1. So this means that this thing is no longer a holomorphic symplectic form. Okay, but it defines a new complex structure. T01 nu is equal to the kernel of this new 2 form. So in the original thing, this was a 2-0 form. So the kernel, the vector fields that interior product to be 0 are the 0-1 forms. But now the kernel of this, whatever it is, that will be my new 0-1 forms, and it will be the new complex structure. So this deforms the complex structure of the cotangent bundle of M to a new one. And this is called the twisted cotangent bundle. Okay. So the result, we call it Z. This is a holomorphic symplectic manifold. It has a holomorphic submersion to M with the complex structure. And it is an affine bundle, no longer a vector bundle. It's a bundle of affine spaces. You can think of it like this. This is Z. Okay. Okay. Notice that. The third thing that I want to mention is that the 0 section in T star M is no longer holomorphic in Z. So the 0 section used to be a nice holomorphic submanifold inside here. But once I deform, the 0 section is some C infinity cross section of the affine bundle, but it is not holomorphic. No, no, it's not a real form necessarily. In some cases, it is. And okay, and I just want to mention that if I take this new holomorphic symplectic form and I restrict it to this 0 section, let me call the 0 section curly L. Then what I get is the restriction of omega naught, which is 0 on the 0 section, plus the restriction of this, which is going to be just omega. So I get a real 2 form. Okay. So the point is that So that L, this is the important thing. So L, I should write it in red if I have red. So L is a Lagrangian for the imaginary part of omega, and it's symplectic for the real part of omega. Okay, so what's happening is that the new space, this new complex symplectic manifold, has a C infinity cross-section. It's no longer a complex submanifold. And if I take the holomorphic symplectic form and I restrict it here, what I get is the Kähler form, which is a real form. And so this means that it is Lagrangian for the imaginary part. So it's a Lagrangian submanifold. But this Lagrangian submanifold is really special because when I take the holomorphic symplectic form and restrict it to it, I get the Kähler form. So this is a new way of thinking about, it's an alternative way of thinking about Kähler structures. So this was Donaldson's view of a Kähler structure. It is a Lagrangian in Z, imaginary part. So you can think of a Kähler structure as a Lagrangian submanifold in this weird space. That was his viewpoint. And this is, he didn't realize it, but he was giving further evidence for Alan Weinstein's famous dictum, everything is a Lagrangian, including a Kähler metric. A Kähler metric is a Lagrangian submanifold, but of a special space, which is called the twisted cotangent bundle, twisted holomorphic cotangent bundle. Okay. So this L inside Z, this is a Lagrangian brane. It's fashionable to call Lagrangians branes because they're boundary conditions for the A model in physics. So they're elements of the Fukaya category. Okay, so it's an object of a category. Now, but of course, this is not the only. Let me just list now the output of this new viewpoint. Is that I have a Lagrangian submanifold of a symplectic manifold, which is an object in a certain category. Let's not worry about the details of this because that would take up the rest of the talk. So the other output that we have is the real part. Okay. So the real part on this whole space is what's called a coisotropic submanifold. Actually, Z just by itself is coisotropic inside Z. That's just a stupid comment. But the fact that it's equipped with this two form, this is usually goes by the name F. Okay? This is a coisotropic A-brane, which is also an element in this Fukaya category. So normally, when people speak of objects of the Fukaya category, they refer only to Lagrangians. But it's been known for more than 10 years. Actually, it's almost 20 years that it's been known that there are other objects in the Fukaya category, and those are coisotropic objects. Okay? And these coisotropic objects are not you're not allowed to put any coisotropic. They have to have a two form, and that two form has to be such that when you add, this two form to I times the symplectic form, it's supposed to be holomorphic symplectic. Should be holomorphic symplectic, which of course is no surprise to us because that's how we built it. But the idea of a coisotropic A-brane is that the two form, this two form, must combine with the symplectic form to give a holomorphic symplectic form. Okay, and so we get another object in this Fukaya category. Okay. And the remarkable fact is that this space that we're looking for, this vector space, is actually the Hom in the Fukaya category of the imaginary part of omega between L and Z. Okay. So this thing, which we normally would use complex geometry to compute, can be computed as a homomorphism in the Fukaya category between a Lagrangian and a coisotropic A-brane. Okay. Why do I put this in quotation marks? The reason is because for the people who study the Fukaya category, they've banished coisotropic A-branes. They don't want to hear about them. They just put them in the attic and lock the door. They're like the Jane Eyre of the Fukaya category. Okay. So they don't have a definition of this Hom space. Okay. But there is a few papers. There's a paper of Witten and Gukov. There's a paper of Witten and Kapustin. And there's a paper of Aldi and Zaslow, where they compute from first principles what this homomorphism space is in what should be the Fukaya category. So they provide some guidelines on how to compute this potentially. And so so the problem here, now the problem is how to define such a Hom space. Okay, that's a major problem in symplectic geometry, which people have not really spent enough time and effort on. Okay, so what our proposal is, so we have a proposal for how to compute this. And let me just briefly explain.
These coisotropic A-branes,
Yes.
they can be codimension greater than 0, or
Yeah, they can, yeah. And I'm not going to talk about those. The one that occurs here is space filling. It's the whole space. But of course they can be higher codimension. They can be higher codimension, yeah. And they appear everywhere. There's a lot of them. But the question is, how do they fit into the Fukaya category? That's an unsolved problem, which has been posed directly to us by physicists. And so far, there's not much progress. So I'm going to give a proposal for how to compute this. Okay, but it's a very incomplete proposal. So incomplete. Okay. So let me explain. So U is a holomorphic line bundle. So what I can do is pull U back to Z. So I get a holomorphic line bundle on Z. And U came with a connection. So I can pull back the connection. But if you remember, the connection on U had curvature omega. And so this will have the curvature pullback of omega. So this has curvature is equal to pullback of omega. But the form that I have is the canonical form plus the pullback of omega. And this is d theta plus the pullback of omega. Okay. So what I would like to do is to modify the unitary connection so that it's no longer unitary, but has curvature exactly this. And in order to do that, I just need to add theta. So I take the connection, which was provided on U, the pre-quantum connection, I pull it back to Z, and I add theta. Then the curvature will be this thing. So we have U, and let me call this D, this sum of two pieces. So UD over Z is a pre-quantization of omega. So now the holomorphic symplectic structure is pre-quantized by a holomorphic line bundle with a holomorphic connection. Holomorphic line bundle and a holomorphic connection. It's different from the usual geometric quantization where you would pre-quantize a real symplectic form by a unitary connection on a Hermitian line bundle. This is different. This is a holomorphic line bundle with a holomorphic connection whose curvature is this. Okay. And then we do the same thing as we did before. We're now going to take holomorphic flat sections of this. And we are going to fail just as we did before, that this has curvature. So we cannot find holomorphic flat sections. Okay? So we cannot find holomorphic flat sections, but what we could do is choose a polarization. We need to choose a holomorphic Lagrangian polarization. Okay? And take, okay, so this is now a different type of polarization. I spoke about a complex polarization before, where we took holomorphic sections. But now I'll take a Lagrangian polarization. So when you have a foliation by Lagrangians, the reason why we want a foliation by Lagrangians is because when we restrict the curvature, omega, when we restrict the curvature to this Lagrangian, it's 0. And so I will be able to find flat sections here, as long as the flat connection on each leaf has 0 holonomy. So what you have to do, as usual in geometric quantization, is you need to ask about every Lagrangian. You have to say, if I restrict my pre-quantum line bundle to this Lagrangian, okay, fine, the curvature is 0, but what about the parallel transport? Is it trivial? So can I find a flat section? And this criterion is known as the Bohr-Sommerfeld criterion. So what you're looking for are Bohr-Sommerfeld leaves. Bohr-Sommerfeld leaves. So you have some Bohr-Sommerfeld leaves. Okay. So we want to take, okay, so the proposal is to take flat sections of U, holomorphic flat sections of U along the Bohr-Sommerfeld leaves. Okay, so which Bohr-Sommerfeld leaves should we take? Well, the question, what are we trying to compute? We're trying to compute the homomorphisms between Z and this Lagrangian. And this Lagrangian is something like this. Let me draw a picture of it. Say it's like this. Okay, so in order to compute the homomorphisms between L and Z, what I would like to do is to take sections of the pre-quantum line bundle along this Bohr-Sommerfeld leaf, this, but not this one. Because I only want to consider the Bohr-Sommerfeld leaves that actually intersect L. Why? Because in the Fukaya category, when you take Homs, you always are computing intersections of Lagrangians. Okay? So which intersect L. Okay? And that's the proposal.
What about the dependence on the Lagrangian polarization?
Unknown. So far, we've investigated a number of examples. I'll explain the examples in a moment. And in all the examples, we seem to get a good answer. And in the cases that we have more than one polarization available, they agree. Why do they agree? Unknown. The physicists would say, oh, well, of course it agrees. It's just homomorphisms between two objects in the category. It doesn't matter how you compute it. Okay, but how do you know it's well-defined? Unknown. What are you going to do? Yeah, it requires a proof. Another possibility, which kind of one direction that I'm going in, is that maybe the objects should be equipped with a polarization. That the object should be actually not a coisotropic A-brane, but a coisotropic A-brane with a polarization. And then the physicists would disagree with that. They would say, no, you shouldn't have to choose a polarization. It should be independent. Okay, fine, but maybe there are edge cases where it really does depend and they're not considering that. I don't know. Okay. Okay, so so this is the proposal. Okay, so okay, and then okay, and then so this is how we would write the quantization of a single symplectic form, right? But remember that what I had to do was to take omega, quantize that, then take 2 omega, quantize that, quantize each multiple of omega, and then make an algebra out of that. So what about the algebra structure?
But already for one vector space, okay, you take those intersections and then what? What's the element?
You take the sum of the space of holomorphic flat sections along all the Bohr-Sommerfeld leaves that intersect L. You get some big vector space, and that's this vector space. That's it. Okay. So what is the algebra structure? Well, okay, then it becomes kind of cool. So if I take U, so if I take my pre-quantum line bundle and I tensor it n times, okay, then if I go through this whole procedure, remember what I did was I took this, this curvature is omega. I used omega to deform to do the twisted cotangent bundle by the magnetic term. So if I do it n times, then I have to twist the cotangent by n times omega. And what I will produce from this is the nth twisted cotangent bundle. Nth twisted cotangent bundle. And it will be equipped with a holomorphic symplectic form, which will have n times the Kähler form inside it, and it will have the zero section will be one of these Lagrangian branes. So we get a sequence of these holomorphic symplectic varieties with 2 objects. Each one of them has 2 objects, the Lagrangian and the space-filling brane. Okay, and then we have the addition on the cotangent bundle, okay, which is a Lagrangian relation. This is a Lagrangian relation. Okay? And that means that if I have an object, a Lagrangian in T star m, and if I have another Lagrangian in T star m, then I can take the convolution of those Lagrangians, and I get composition of Lagrangians with the Lagrangian relation, and I'll get another Lagrangian in T star m. So what this means is that the Fukaya of T star m is monoidal. Okay? If I have an object and another object, I can add them together and produce another object. And the objects, so the construction is functorial. Okay? And what I mean by that is that if I take this Zn and I convolve it with Zm, then this will be isomorphic to Zn plus m. And if I take the objects inside it and I tensor them, I get they're compatible with the monoidal structure. Okay, and then according to the yes, of course, yes. And so in this case, in this example of the Kähler structure, and in the only example that we've been able to compute beyond this, that is fine. That happens to work. But in general, yeah, it's a major problem. So this would imply that Hom from L to Z and Z, that we would have a map, to Hom L m plus n Z n plus m.
Not symmetric, or is it symmetric?
It's symmetric in this case. Yeah, yeah. So in general, you should expect that the Fukaya category of any symplectic groupoid is monoidal, because there's a Lagrangian relation between G cross G and G. Okay. This also has not really been that well studied, although there are some of Denis Auroux's students who have been looking at this. Okay. So as a result, we should get a tensor product like this. Okay. And this is exactly what we need. This would be HM, this would be HN, and we would get a product structure M plus N. So this is the replacement for the tensor product of sections of L, of U, of UM, UN, UM plus N. Okay. So now we've taken the vector space and expressed it as a Hom space, and then we've taken the tensor product, the product on the algebra, and expressed it in terms of composition in the category, or this kind of double composition, or however you want to call it. Okay. Okay, so this is the proposed solution to the problem. Okay, so in general, what we need to do is produce a sequence of holomorphic symplectic spaces, each of them having two objects in them, something Lagrangian and something space-filling, and each of them I can take a single Hom space, and then I have a sequence of Hom spaces, and they have a tensor product. The tensor product comes from the composition in the groupoid. Okay. So I hope that it's clear that I hope that you can see that it's possible that this whole thing can deform. So that if we deform T star M to a symplectic groupoid, we still will have this idea of a holomorphic, well, I'll explain exactly what I mean, but all of this structure should continue to be present. This will be the product in the symplectic groupoid, and I will still get this algebra. And the cool thing that happens is that when this deforms to a symplectic groupoid, which is non-trivial, like not the cotangent bundle, then this algebra will become non-commutative. And that's the mechanism by which the thing works. Okay, so I've told you basically what the idea is. And the reason that the idea is somehow incomplete is simply because of the fact that we need to be able to compute those Hom spaces, and the people who work on Fukaya categories don't tell us how to do it. So we need to invent a proposal, and the proposal is incomplete. Okay, but conceptually, this is what the proposal is. Okay, so let me just explain. Oh, so I kind of ran out of time already, because you're supposed to ask questions now. But let me very quickly explain the example that we were able to compute with Francis. So the example is that we take a toric Kähler manifold, Mi omega. So we have a Tn acting on M omega, and we have a moment map to Rn. Okay. And so, right. And then, okay, and the point is that, that this twisted cotangent bundle, so there is a C star action on Mi to the n. So this torus action, it complexifies to a toric variety structure. So it becomes a complex torus action. But this is not Hamiltonian. Okay, but on Z, the C star to the n action becomes Hamiltonian. It is Hamiltonian. It is holomorphic Hamiltonian. And this is now a holomorphic moment map for the complex torus action on Z. Okay? So this is a toric variety in the usual sense, and it becomes complexified to this Z space, the twisted cotangent bundle, where I have a holomorphic torus action with a moment map. And the fibers of J are a polarization by holomorphic Lagrangians. Okay. And the Bohr-Sommerfeld leaves are exactly the values of the moment map, which are z to the n, sitting inside c to the n. And the Bohr-Sommerfeld leaves, okay, and this is the key point, is that that if I take J and if I restrict it to the Lagrangian which sits inside Z, what I get is the moment map, the original moment map. Okay, and so this means that the Bohr-Sommerfeld leaves, which intersect L, are exactly the integer points in the Delzant polytope. Okay. These are the values of the moment map, of this moment map, and they give me a sequence, a finite set of holomorphic Lagrangians, and I can take sections along there, and I get the homogeneous coordinate ring of the toric variety. Okay, now, so this example is going to produce the homogeneous coordinate ring of the toric variety. And so, so you're going to get a commutative algebra, which is the algebra of the toric variety. Okay, now we go back in the literature and we see that there's a very nice paper of Ping Xu, and there's a paper of Xu and Weinstein, where they study Poisson structures coming from R matrices, C, wedge 2 of the Lie algebra, C is equal to 0, and the Lie algebra acts on M. So if you have a Lie algebraic Poisson structure, and the Lie algebra acts on M by some action, then you can push forward the R matrix, and we get a Poisson structure. In this case, we have a C star to the n acting on M. So we get this Poisson structure, which deforms the complex structure to a generalized complex structure, J. Generalized complex. Okay. And what they explain is that everything goes through so we follow Xu, and we see that Z, the union of Zn, is a symplectic groupoid. And I'll just write one formula where where all the structure remains the same, is unchanged, okay? But the projection map to M deforms to two maps where pi plus minus has this very beautiful formula, e to the plus minus 1/2 c of j alpha. Let's say if alpha is a point in Z. Okay, and then pi of alpha. So the idea is that now we're going to deform the structure maps of this Z space. And the way that we deform it is that we take a point in Z, project it to M, and then we act on it by a group element, and the group element is obtained in the following way. We look at the value of the complex moment map in the dual of the Lie algebra. This dual Lie algebra element is contracted on the R matrix, and that gives a Lie algebra element. Then we exponentiate that, plus for plus pi plus, and minus for pi minus. And this gives a symplectic groupoid structure. You could actually think that this flow is the result of doing the spray of Jonut and Kreinig. Okay? The spray construction of the symplectic groupoid. And this is still the symplectic groupoid. So what this means is that J is unchanged, Z is unchanged, omega is unchanged. The Bohr-Sommerfeld leaves are unchanged. Everything is unchanged, except for the product. So everything is unchanged, except the multiplication law on the union of the ZNs. And what happens when you compute the multiplication is that the convolution is non-trivial. And you get an algebra which is a sum. Let me just write the product fnw2 is e to the minus I pi c w1 w2 fm plus n w1 plus w2. So the w's are the points in the integer points. N is the degree. Okay, so if I take an element in degree m, which comes from the weight w in the Dalzant polytope, and I take another element in degree n, and I take their product, then I get the element in the sum of the degrees, the sum of the weights, but it's multiplied by this factor, which depends on the R matrix. Okay, and as a result of this, we get a non-commutative algebra, which on the interior of the toric variety is the quantum torus. So what we get is the complex quantum torus compactified to a non-commutative toric variety. Anyway, I'm sorry that I took up all the question time. Thank you for your attention.